So name one.
I don't know. I think I'll still
Numbers, yeah. That would also just like all the different movements.
But I always forget which numbers are which.
Go.
When is the next exam?
It's on the web.
It's
on the thing. Is it on the class schedule?
No, that would actually be crazy.
Get the quick answer for me.
I don't know.
November 1st.
I just work here, man. I'm a slave to that, whatever that schedule says.
That's crazy.
Here.
Yeah. Yeah.
Friday. Morning at 3. Just get rid of the white space, make your mind.
Small world. Jeez.
Shrink the font.
I only did the amount of paragraphs they said.
Okay, let's get started. Actually, there's one thing I should show you. Let's see. So homework 6 is up. I extended it by a week because you have spring break, or not spring break. It's fall study days. I always interpret that as you would take time to study. I have learned that students take that as a break from studying. Conceptual difference between the professors and the students. It's just fine. Now I'm learning. So my compromise was I wasn't going to make anything due, or I just moved homework back a week. So if we go to the schedule, that should be reflected there, should be reflected in Gradescope. To your question, exam 2 is on the November 1st. Okay. Your next little bit of assignments are the week we get back from, or you get back from wherever you've gone for your study break, is we have you're gonna have meetings with me, Matt, and James, or some combination of that to review your project proposals. So you need to go ahead and sign up for project proposal time. Those are the times that we are available, okay? So some of those are during class time, so if you're quick, you can get those. Some of them are not during class time, but we wanna make sure we have a half an hour to meet with each group. We're gonna go over your proposal. We're gonna answer your questions and give you line of sight so you know how to build whatever it is you're gonna build. And maybe if it's too ambitious, we'll pull you back a little bit. If it's too easy, we'll add a little something to it. So that's the goal. So that's next week's assignment is you have to have the before, see, somebody's getting in there. They're going fast. The night before your actual meeting, you have to have your proposal in your project folders, which I'll make tonight after everybody's supposed to sign up. So every team is supposed to register for their team tonight. That'll tell me who's I'm supposed to share the folders with. All right, so any logistics questions here? So anyways, next week, these times, that's when your proposals are basically due and you're gonna meet with us. That's the next thing. Okay. All right, we didn't quite finish off serial buses last time, so we'll do a quick review. So we talked about UART, we talked about 3 3 specifically. So UART, this one was a completely asynchronous bus interface based on kind of old technology that's been repurposed for PCBs. There's no idea of a controller. There's no idea of a peripheral. They're both equally independent, can initiate conversations back and forth, which is nice. Of course, both have to be set up and ready to receive, but so either one can transmit whenever it wants. It's fully duplex, so you're not going to get any collisions on those channels. The challenge here is this asynchronous, so we had to do that clock recovery thing, right? And that was the clock recovery. Any questions about UART? I'll do a brief overview of the three things. Okay, here we go. So SPI, this has a dedicated line. This is much more of a bus structure, so in the sense that it's meant to talk from one controller to talk to many things. And bus lines like the data out of, or data into the controller, the data out of the controller, and the clock are all shared, so you get to a bunch of reuse there. The way we do arbitration, though, is we have a chip select line. So when that line is pulled low, you're going to select the chip that's supposed to be talking, or supposed to be listening or interacting with. You could, if the chips allow it, talk to multiple things at once, but your chips would have to be set up for that. You have to look through the data sheet to say that, okay, that would result in correct behavior like you expect. You wouldn't want to select two chips to access and be expecting both of them to talk back at the same time. Then you get collisions on these lines here where both of them would try to be pushing ones and zeros onto this bus, and that wouldn't work. But you could certainly transmit to all of them if you wanted to. One of the challenges with this one is that you had those multiple clocks. You could look at the phases, polarity and phases of the latching in the clock. So it's a piece to keep track of. And then there is no set real spec for this. You'll see packet sizes from 4 to 16, but typically they're 8, at least for the things that you look like in this lab. But people reuse SBI for all sorts of things. So there's a CSBI, I believe, which is a camera version of SBI. They actually have more data buses, and those are hundreds of bits long packet sizes because they're trying to push camera data through this bus interface. So people reuse it for other things. Questions? Oh, just so waking up, that's fine. No worries. I squared C was the other one. Sometimes they say I2C. This is the version where you have everything is on just 2-wire buses. I mean, you always need ground, so one for data, one for clock. And the peripherals are reusing the data line for transmission and receive. So this is the challenge of, because it's this open collector output thing, you don't specifically know which one is talking just by looking at the line. You'd have to walk yourself through the protocol to see who's supposed to be responding. The open output ring allows you not to have collisions, which is nice if 2 peripherals or 2 devices started to talk at the same time. But the challenge here is that you always have these resistors, and those resistors are nice. It keeps you from having collisions, so now you can have lower number of wires. That's great, but speed of your bus is now defined by those resistors. There's a maximum speed that the smaller the resistor, meaning the more current it can pull, the faster it can go. But now you've made data rate and power inverse to each other. So that's like a weird trade-off to think about. This one is not specifically shown here, but you can have multiple controllers on this bus. They have to negotiate a little bit and just check the bus isn't being used. And arbitration is done through addresses. So each peripheral device will have an address that a controller will specifically talk to. And typically address bits and data bits are 7, 10, or 16. Remembering this? Okay. So we can look through some of the pros and cons of each one, right? So UART's nice, it's 2 wires, but it's only 2 devices. It's pretty limited. SPI is 3 wires plus, so that's data out, data in, and clock, plus N wires for N devices. And the topology here is 1 to many. And then I squared C is 2 wires, and the topology is 1 to many or even many to many. Depends how you look at it. Arbitration schemes are there, and the timing method. And then I coarsely said simplicity, right? So UART's pretty simple. SPI is, I would say, middle of that because you have multiple devices in there you have to deal with. And I think I squared C is higher, but you get the benefit of lower wires. So your exercise is to figure out how would you make a 1-wire interface. So we're going to make a system that only has 1 wire. So why don't you work together? You can use all those tricks we talked about before to try and figure out how to make a 1-wire interface. Now, of course, there's going to be ground. It's important to think through serial communication to figure out what sort of interfaces there are. All right. Find one? Go get one. So part of the assignment is to fill out this topology. You'd probably want to maximize things like topology, or you want to maximize if you have multiple variables here, but fill this out and come up with a plan. What would this bus architecture look like? How would you resolve things like timing, arbitration, what's the topology, what's the speed do you think you get out of this? You can draw some circuits if you get real excited. You're all like, I did not expect to think. Horrible. I wanted to be entertained.
What is it? Is that like
Topology. We could have a hub and spoke or a star topology. We have one controller.
Yes.
I squared C you could have multiple controllers, so it's N controllers to N peripherals. And UR is always one to one.
What's the I squared C thing?
I know, I need to wake up. I need to get up.
New hamstrings so that you have to do asynchronous. So UR needs to drive the same. It's connecting.
All right, so if you have one wire,
But that's 2 lines.
what do you have to do for timing methodology?
Asynchronous.
All right, so you're not so sleepy. Okay. How about arbitration? Okay. Start drawing some circuits. You can probably figure out the entire hardware for what this is going to be. Think about I squared C and SBI. How would you get this done?
Arbitration is how you decide.
Too much of like UR is it has like I guess if you have one line, it's kind of like
It's a reader, right?
In case of one wire, you can't like. There's cases you know arbitration.
I squared C.
Right.
that's my level.
You really just do like I squared C, but
Yours did, so I don't know how yours is working.
there's my art.
I had no idea.
I couldn't even download it.
Yeah, so like,
I know, but it's corrupted and I can't even open it, so. Sorry. I can't open this, but,
Yeah, that's what I'm saying.
I was just thinking like a
no, it was pretty easy.
I'm trying to think of what has to change.
Mine,
I did my private account.
I think it has one third.
the reason mine didn't work was because I was running it on CPU.
No, it's true.
You could like have changed.
You send like one at a time, I guess, right?
or something.
Like there's 2
Yeah.
wires.
But I think this is down.
Some sort of
Say packet header. Acknowledge.
I squared C need 2 wires, right?
Just I to C, but it's like one.
They want to.
So where? They have to send the back.
The like USB peripherals are set to receive and then header.
Like there's send.
So how are you going to do
question?
simple line going to be?
They basically just flip it. Yeah.
How do they know when the next bit is sent? You just have your low voltage be higher.
You have to draw the internal line.
All the slaves.
You could do that.
Great. And you can only start.
It's like a tri-state. It's like there's a power state and there's 2 states on top of that.
It's kind of.
Draw that out for me.
You can make it like they'd agree on a bunch
Basically,
of
the set
everybody agrees on what baud rate and all that. Okay.
like a one, it's like a long one or a short one.
How's it go?
Scanning, so I was like, okay, 7 hours before.
Send packets.
Just dinner. You went
Sitting state and I just like what's that?
How'd you do with power? I want you to, the bonus here is
you're not supposed to eat the food in your stomach.
not to have any power connection.
Pretty sure they say you're only supposed to. Yeah.
Basically, you're just more asynchronous.
I don't know.
You need to sync the clock, right?
We're thinking.
Of the
So you can have like synchronization bits, right?
Fantastic. Big improvement.
You just think
One wire.
There's one wire.
Okay. Think about how you work those things.
Yes, inverted.
Pull it up. I got it right here.
That's like
How you guys doing?
like the other side samples.
Anybody figured out how to get the bonus part there?
It's all it's the mid bit.
How are you gonna make this thing send power as well?
You have a capacitor.
Well, it's a good thing you're looking at Lucas.
Draw that data out for me. I want to see. I want you to invent the future.
No, I did not.
What's your name, James? Oh, another one?
She's all violent.
Have a large enough capacitance so like.
All right. The other challenge for everyone is how are you going to send power through this thing? I want that peripheral to have no batteries, no power lines whatsoever. So I gotta send data, you gotta send clock and power, and you only get one wire. That's it, and I'll give you ground. Can't use it for anything really, but I want everything done with one wire.
And then let a capacitor on the other side charge it up for a while.
You
And
actually
then you
want
start transmitting the
two
data
wires.
and hope that the capacitor doesn't run out.
And it looks like one wire.
It's a PWM idea. There's something there. I like that.
Is there something about PW?
Yeah.
I'm gonna do. Know when to push the kid in the swing. That's not a statement about synchronization, right? So remember, know when to push my hand.
This I was not a person when he's
Like which way transmission is going, right? So that they're not both transmitting or both receiving.
So it's constantly high, right? So it's charging up.
I like that. Draw that down there.
Transmission starts. It gets brought low, and then it does PWM at a known period. Set beforehand on both, right? And the is discrete, so it's like, or the PWM is discrete, so it's like if it's within this range.
It would technically work. We'd have to figure out how noise would handle it because your noise margin between 0, logical 1 would be smaller, but it could work.
Yeah.
Values.
Maybe 8 goes up to 8, and it can transfer.
What if,
All right, we're ready?
so they're gonna be
Let's review some here. All right, so this is an actual standard. It's called one wire. All right, you can go buy parts with one wire. You have a host device, which is basically just a NMOS, or an open drain, and it's got an inverter here to take whatever data is coming in this way and threshold it and put it into the port. It has a topology here of one host or one controller to many devices. I don't see why inherently you couldn't make it multi-device or multi-controller, but this spec is N-to-1. And then the receiver here, you got an NMOS as well, and a gate, a thresholder here, and so everything has an address. So that's how arbitration is done with packets headers. Everything's done asynchronously, so you're going to have to go and have your header, your first bit, just like UART, helps define what the length is of the symbol coming in, helps you understand when you're supposed to sample the data, or equivalently when you're supposed to push the kid in the swing. Speeds are kind of low, and complexity, I guess, is simple. It depends how you define complexity. And how are you guys going to do? So here's how they do energy harvesting. So on this pin here, they just have a diode into a capacitor. So you have to put a 1 out for a while, and then that charges this thing up. And then you can do logic. You can modulate this thing, and that capacitor will store energy on it while you're getting dips in your data, so the thing stays on. I can show you some example of that. I actually don't have the harvest. Oh, do I? Oh, I do have harvester in here. Hey, that's a smart guy. Okay, so let's put a 1. Let's see what I got. I'm gonna put a 1 on there. So here we see this node is charging up. vHarvest is charging up over time, right? And if I put a logical 0 back on there, it started discharging very fast. Why did it discharge so fast? Is that harvest? No, harvest is blue, so that's still high. Right, and it's still high because I don't really have any load on that capacitor in this simulation, so I'll just put some load on that capacitor, and we'll just watch it discharge. You might be saying, like, what the heck is that load you're talking about? Maybe this is the equivalent load of all the circuitry here, right? So it's going to consume some power just to be on and understand the state. Maybe it takes a temperature read. So here, the little red line is the power, and what I'll do is I'll turn it on, it charges up, okay, and then I turn it off. This is the voltage on the line here. That is what this thing is. Where's that one? Oh, here, V-bus. So this is the data on the bus. The red is the power on the bus. So if I charge up and I go very fast, you can see, you can't see very far back there, but I can see, because I'm very close, that I was able to send bits quickly without the power discharging all the way. Okay, so now I have a device that can harvest power and power itself, theoretically, and then I can send data back and forth doing the same techniques as I2C. So I'll run this some more. We're still charging up, and then the device here can send data back. And you can still see that power is didn't get discharged too quickly. So here we have the transmitter sending data, we have the receiver, or sorry, the controller, the peripherals sending data over here, and then you'd have to have some bit sizes that you were expecting. So the data sheet's going to tell you, hey, these are the sizes of the bits, how long they're supposed to be down for, and you have to do some clock recovery, probably on the first symbol here, to figure out where the time is, where the phase is when you're supposed to sample inside these little bits of packets. What do you think? Any questions? Yeah.
Is this common for peripherals to use one wire?
No, not really, because a manufacturer would specifically have to make chips for it, but it's not. So it's not as common as I2C, UART, and SPI. But you can go to DigiKey and buy a bunch of chips. So it's typically like really pin-constrained devices that want to use these. I don't believe your STM32 has a one-wire peripheral on it. But you could, you could trick your UART into doing this probably somehow. You could bit bang it yourself if you really wanted to. Yeah.
How do you control who talks to who at one time?
So in this case, in this protocol, you have a controller that's doing all of that. So the controller would have a start sequence. So first it powers up the peripheral. I have to read through the whole spec. I think the peripheral, once it's charged up, pulls the line down once for a short period of time, saying that I'm here. And then the controller says, okay, sends out an address and says, okay, I want to talk to you. So then the rest of it's just like I2C. Yeah.
Why are there 2 knots? At like the input wrenches.
Oh, up there? Yeah. That's just my buffer. So you don't need them. That's just false sad logic here. So basically, I wanted to have this is just an indicator that says high or low. So, and this is an analog signal. So I wanted something that will thresh it high or low. So I put an inverter in here, but then I will confuse you all if all the logic's wrong. So then I put 2 in them to confuse you on why there's 2 inverters.
Because you need to be charging up the power capacitor
Yep.
in the target, does that mean the bus needs to have a small pull-up resistor? Or could you do this with like if I was to be like 10 Kerosene instead, would you risk the target losing charge?
Yeah, I bet I'd have to look through the details, but they define a particular capacitor or resistor you're supposed to use. But you're right, if that resistor was too large, meaning it couldn't put current through, then the charge up time here would be small, would be much longer, right? So we can actually, let's simulate what that looks like. I have a simulator. That's gonna be a lot. Let's see what happens. And so this isn't even enough to supply enough current for that 10K load. You can actually see that it's just going down. And so let's go over here. And now, oh, look, it's slowly rising up. So let's increase the simulation speed up to here. Oh, come on, you can do it. Go way forward in time.
Voltage divider, so it's not gonna.
Oh. You're electrical engineer over there? Fantastic. Computer scientist?
No.
All right. Whew. The computer scientists are calling me out on voltage dividers. I'm in big trouble. I lose my job. But he's right. I made a voltage divider between here and here, right? So this voltage can only come up to VDD over 2. So anyways, yes, the amount of current it drives will basically demand that those transitions, the pulses, are much, much smaller.
So does the spec say, like, do you have to decrease that resistance even more the more targets you add? Like, if I had, like, 20 targets on one wire bus, would I need, like, a 500 ohm resistor instead?
I don't know. I have to look it up. I've only thought about it. I've only seen use cases where it's like this one device, but they do support multiple devices. That's a good question. Yeah.
Is there like a formula or like a method for people determining how fast their protocol needs to be? Like in this case, it has to be like agreed upon for both, but like, what's constraining that?
So why can't we just go infinitely fast?
I mean, there's like capacitance and stuff like that.
Yep.
Is that the only thing that you're kind of looking out for there, or is there like digital stuff happening too?
So from the bus structure itself, meaning the wires outside the chips, yes, it's really just the capacitance. Trying to go really fast is the structure of the wires. If you get up past like 100 megahertz, they start acting like antenna transmission lines. So the structure actually matters, but you're probably going to be limited by how fast you want to be switching here first. So running this thing at 100 megahertz is like going to consume a lot of power, and you probably don't want to do energy harvesting.
But it's not like something where you'll give us like a thing. It'll be like, how many bytes can you transmit in a second? Like that's beyond scope, right? It's
I don't know. I'm getting me excited.
Like you're having us write there's like a box for speed. So you mean like fast, low, or whatever? Like
Yeah. That's fine. I would make sure it's well constrained. I'm not gonna. If I asked you an open-ended question, it would probably be which one's faster or slower. Not can you give me an absolute number? Because you're right. It would be very hard for you to say this is 10 kilobytes or whatever. That is just what this particular spec does.
Gotcha. I see. Thank you.
Yep. All right, any other questions about one wire or serial communication in general? Okay, great. You don't want those. Those are old announcements. All right, so now we're going to talk about the world of analog. This is the last big section of 373 from like a lecture material point of view. So we'll start off with just a little bit review of analog circuits, or at least signals, that you would kind of need to understand this material. This is, I don't know, I think it's when you guys talk about Fourier transforms, and is that 216 here?
Yep.
Okay. Don't tell any of those 216 professors I'm teaching this. They'll get mad. They'll be like, he's doing it all wrong. I'm just trying to teach you enough to get through 373. All right, physical world. So what do we need to do? You know, what's the goal here? Oh, come on. So we have this world that's really good at doing computation, but all the important things are out here in the real physical world, and most of them they're analog. So sensor input, sound, actuators, listening to sound waves, all those things are analog. And our primary way to look at these things are analog digital converters, which is basically a microphone, you can think about it that way, which is going to sample some analog signal and turn it into some digital one. And the converse is a digital to analog converter, which is going to take some binary values and output an analog voltage. And you're familiar with these things in the abstract, that these both components make up most of your sound audio equipment. So your earbuds have DACs and ADCs in them. That's how they work. The corollary to these what you would see in the lab is oscilloscopes and function generators. These are just fancy versions that are doing arbitrary waveforms, while these do very specific ones. These are at particular voltages and frequency ranges. These go up to much higher frequencies and wider voltage ranges. So sampling rate is just the rate at which you are making a digital measurement or putting out a digital voltage, and how often that is updated. So for example, CDs are 4,100 samples per second. Okay, does anybody know why they chose that? Of all the frequencies to sampling rates, why was that chosen?
The hearing range of the human is 40 or 20 kilohertz.
It's 20 kilohertz.
Yeah, and then it's 2 times plus some.
Yep, 2 times. Now so that's like, so 20 kilohertz, so usually the rule of thumb is humans can hear from 20 hertz to 20 kilohertz. Most of you, babies, can hear the 20 kilohertz. Most of you young folks are probably still at 18 kilohertz. My hearing test says I'm at 12. Welcome to old age. I also have a daughter. She is very loud. This would be medium quality, right? So maybe MP3 or something. Low quality audio is going to be 22 samples per second, about half of that. Phone is only 8,000 samples per second. Why is that? Humans just don't make high frequency sounds. Like, yes, you could sing or make a high frequency sound, but that's just not part of speech. And so to be understandable by other people, we just don't need that high sampling rate. And why did, say, AT&T back in the day make this decision? Why not just go up to the full hearing range? What was their constraint? Yeah, well, and then before they got to the money constraint, what was the other constraint that cost something? Bandwidth, right? So they had to make a decision. So all the cellular networks had to make this decision too. Do they want to have just one person at 22 kilohertz sending audio, or would they like to get 2 people in that slot or 3 people in that slot, right? So it's just money came down to, well, humans aren't very good at detecting things, so we're just going to give them lower audio bandwidth, and that will be fine. Sometimes you hear really poor quality audio, and you'll find out that it's actually like 4,000 kilohertz, which is just like poor, yeah.
Do modern phones have different sampling rates depending on what you're using? So like call someone.
Right.
Is that sample rate, 8,192? If I'm like playing a video, is the sample rate?
Yeah. So and it's also like where in the phone did it get changed, right? So your microphone is probably going to be sampling at 44,000 samples per second, which can capture 22,000 samples. Our audio frequency is up to that frequency range, sorry. But when it gets to your modem that's trying to send data over cellular, it probably gets downsampled because they want to conserve audio space. Likewise, your speakers can't really go that bad. Even the best speakers are really only maybe 18 kilohertz in phones, maybe up to 20 kilohertz. So even though it might be trying to play them, you can't hear them. In fact, as an interesting side note, humans can only hear, the best case, right, we said was 20 kilohertz. You can actually, each one of you can hear things that are higher frequency. It just won't make it through your eardrums. So we had a little experiment in my lab where we put ultrasonic transducers here, so they would bypass, and you can hear 22 kilohertz. Doesn't sound very good. I can hear it though. It's amazing. So we were like, oh, maybe we should make a bat signal thing, or like we'll give everybody bat hearing. And so now you can hear ultrasound coming in because we'll just sample it and then play it through your skull in your eardrums. Nobody was excited about that. I was excited about that. Nobody else was excited about that.
Like, could you then theoretically hear the frequencies that bats make? Like, could you then communicate with bats?
Well, you could hear the bats. But in a lot of rooms, they have ultrasonic transducers to do room occupancy to turn off the lights. So those are at 25 kilohertz. So we didn't really see if it could go up 25 kilohertz. But in theory, you could hear those frequencies. it doesn't sound great. Nobody's excited about hearing them. And the bandwidth is pretty small, so you can't get a lot of information through it. It's kind of like it's on or off. Anyway, side note. So we're kind of getting to Nyquist-Shannon sampling theorem. Have people heard of this? Yeah.
Question. So for the last one, like what does the in frequency have to do with each other?
The sample rate and frequency. I'll show you in just a second. So you can have a sampling rate, and then there's like, well, we'll see in a second. In 5 slides, ask me that question again.
Okay.
All right. So Nyquist-Shannon sampling theorem says that to detect, now this is not perfectly reproduce the signal. This is to determine if a frequency exists. You have to sample up to twice as fast, or you have to sample twice as fast as that frequency. So this says this is why human hearing is 20 kilohertz and phone high quality audio is sampled at 400 or 44 kilohertz. So double the frequency. Okay. So here's kind of we'll do a few examples. So if you looked at, so here we have a plot, this is just time, and this is ADC samples, let's say. And so from this, you could probably go through and figure out the sampling rate. So how would you do that? Or sorry, you can figure out the sampling rate. Sorry, the sampling rate is this from here to here, so you could just divide this time, this minus that, figure out the time, and then 1 over that is the frequency. What is the frequency of the wave I just sampled? How would you find that out? What's that? 200 hertz. How would you figure it out? So the sampling rate is 2 kilohertz, if you do the math. The frequency is 200 kilohertz, or yes, 2 hertz, or 200 hertz, sorry. So you go from this peak of this waveform, or this trough, let's say that peak of that waveform to that waveform, divide that time, you get the frequency of that signal, right? So I had enough data points here to recover the frequency of the incoming sine wave. How do we feel about that? Okay. Great. Yep, and that worked out. So here's the problem. What's the frequency of this signal? Well, it could be, are a number of, actually I guess there are infinite number of choices, technically. But realistically, there's maybe 2 choices. What are they? You can just describe them. You don't have to calculate them.
DC.
Could be DC, yep. What else could it be? Yeah.
It like has the exact same frequency as the sampling rate?
Yep. So it could be that. So this is, now you're starting to see the problem with just using Nyquist sampling theorem. So technically, Nyquist, in their theorem, removes DC. They say that's not a valid frequency if you're trying to detect frequencies. And they say, okay, I've sampled it twice as fast, so now I can recover what that frequency is. So that's the highest possible signal I could recover. Now it's true that you could go through and have twice as many the sine wave could be twice as fast. You just wouldn't have enough data points to disambiguate that newer signal that's twice as fast from this one. You don't have enough information. All right, and then here's the next example. If you go, this is if you go very, very fast. Right now I'm going faster than my sampling rate. So here, this is exactly the same frequency. Oh no, don't give it away. So this is 200 hertz, right? But if I go faster, I could still make that waveform if I wanted to. You would still see on your oscilloscope, you would still see this, and you might trick yourself into thinking, oh, this is again 2000 hertz, or yeah, 200 hertz. But if I go much faster, I could fit a higher frequency sine wave that would, when my oscilloscope sampled, would trick me into thinking that that signal was there when it really wasn't. So here's an example where the sampling rate is 2000 hertz, but the signal itself is 2200 hertz. Likewise, you're going to find signals that have multiple frequency components on it. So can anybody figure out what that is? Yeah, okay, go.
It's like this.
Yes? But you, technically, it should be possible to recover that signal. It's just very hard to see it. If you just saw these points to figure out, okay, that's what's connected. Okay, maybe you do some math to figure out the components. And so this is actually, I think this is 100 hertz, 400 hertz, and 1600 hertz all on top of each other. And so pointing out that without enough samples, it is hard to recover what the actual signal is, even though it's technically possible. So that's why I say I'm going to use the oscilloscope sampling theorem. Not the real, it's not Nyquist, this is oscilloscope sampling theorem. So you want to have your max frequency, you want to be going at least 5 times faster on your oscilloscope to recover that thing, because you've got to see it with your eyes, right? This is more practical. You want to have enough points to fill in the dots to see what it is. And so how you figure out how fast your device goes? So here's oscilloscope. This is 200 megahertz sampling frequency. Why is that so blurry? It's horrible. So it says 200 megahertz there. And if I decoded it, 200 megahertz, but 5 gigasamples per second on 4 channels. What does this mean? What is gigasamples per second? What is 5 gigasamples? How does that relate to 200 megahertz? You guys have used oscilloscopes, right? No? Please? You guys have to take 215 for CE majors, right?
Yeah.
Okay. I just wish it was before this class, but I know it's not. All right, any guesses what 200 megahertz means? 200 megahertz bandwidth? No idea. Okay. 200 megahertz here means this is the maximum frequency which this equipment is set up to take in. Okay? So if you put 400 or 300, it will start limiting. It will not be able to faithfully reproduce that signal. The analog front ends here, all of the circuitry, all the path is not designed for that, and probably actually is going to get filtered out. So don't try to use this piece of equipment for things higher than 200 megahertz. The gigasamples, the 5 gigasamples, this says this is the maximum sampling rate of the device. So it can sample much finer. It just can't take in an analog signal that's over 200 megahertz. And part of this is it's going to take 5 gigasamples and divide it across 4 different channels. So you take 5 gigasamples, divide by 4 different channels, you're going to get something like 6.5 gigasamples per channel. I think that comes out to, and that tells you, okay, you can oversample the 20 megahertz each channel maybe by 5 extra samples faster than 2 megahertz. If I did my math correctly. So actually for all 4 channels, if you had all 4 channels on at once, you can sample 4.25 times faster than 200 megahertz. But if you did 1 channel, now you can go 25 times faster, yeah.
Is that supposed to be 5 times or 10 times? Because the
5 times, or yeah.
The slides on the website say 10 times.
Well, it's a made-up sampling theorem. Okay. It's oscilloscope sampling theorem. So I think you should go for 10, but the oscilloscope is at best going to give you 4.25 times x. And they do that on purpose so that you can recover those signals. You have quantization noise. So Nyquist sampling theorem is just going to say go twice as fast, but it's just not enough in the real practical world. I will update the slides. All right, anybody have any questions? No questions. You're like feeling good.
When you look at the spec for an ADC, does it talk about like how much capacitance it's putting on the line it's measuring? Because like I know that's the thing with oscilloscopes is you want to make sure your leads are like really low.
That's a good question. So in terms of samples per second, this is the highest, this is the most significant number usually for your ADCs. And we'll talk about ADC structures in a couple lectures. You can find buried in all the documentation what is the load capacitance of that pin. Most ADCs will have a low-pass filter on the front end so that you cannot actually put in signals faster than it can handle. So now you don't have that aliasing problem. Any other questions? Do you have questions? Fantastic. I knew I was waiting.
Yeah, whether it's sampling may have to do with frequency.
Does sampling have to do with frequency?
Oh yeah, that was my question 5 slides ago.
Sure. So here we have, this is the sampling rate. This is how fast I can sample. 5 gigasamples per second. Okay? How do you feel about that? That seems really fast, right? But so what we're saying here is this particular device will only take in signals that are 200 megahertz. So in some way, conceptually, they're actually separated. You could sample a frequency faster than is required by Nyquist sampling theory. And it's actually, I'm suggesting as part of this lecture is that you do that. Does that answer your question?
So like, if you sample fast enough, you don't have to worry about the frequency?
You don't have to worry about undersampling your signal and not being able to recover it. So if I sample too slowly, I get back to this scenario where I'm sampling slower than my incoming frequency, and I am unaware that the frequency is actually higher. So sampling rate is how fast you sample a given signal. I can only recover frequencies up to 2 or half the sampling rate by Nyquist, and I'm arguing that you should probably do recovers or detect signals 5 times slower than your sampling, not just double. How you doing? Feeling good? Okay. Yeah.
This might be a dumb question.
You don't have dumb questions. I'm literally, my job is to teach you things.
When it says like gigasamples, is that, can I translate to like 5 times 2 to the 30th? Like, is like the frequency?
Yeah.
It's like the sampling frequency,
Yeah.
basically?
It's just they're not telling you gigahertz. Right? Because then that might make you think, oh my, I have a 5 gigahertz oscilloscope. I go put some Wi-Fi signals in there and nothing comes out the other end. So Wi-Fi going up to like 2.4 gigahertz, let's say. You could try and say, I want to directly sample Wi-Fi for some research purpose. This thing won't let you because all the analog here is built up to 200 megahertz. So both these signals, these things are upper limits on what you can, frequencies will go in and how coarsely or finely you can resolve those signals. Okay. So we'll go on to analog digital converters. Their job here is to take these time continuous signals, right, and quantize them both in magnitude and in time. So we're going to have 2 versions of quantization here. And we just talked about the time quantization, because you're only going to get them in little steps where you sample them. And now we'll talk about the limitations on magnitude quantization. So here we have a nice little sine wave and a very coarse analog digital converter. Right? This thing is going to, this table is showing you, here's binary values superimposed upon a sine wave, of course, so you'd have, I guess the other axis should have been voltage. And we're saying that for every sine wave, so say we sample right here, it has to be quantized into some value. So let's just say, we'll talk about the direct math in a minute, but say here we're going to quantize this value to 0, 0, or 1, 0, 0. And then this other value is this other value, right? So we're going to have a representation of the sine wave, but not the sine wave itself. And so the number of bits in your ADC makes a big difference on how well you can resolve that signal. Because when you take this, you say you take this value and you plot it, it's going to look pretty chunky, especially if you have a lot of variations. Maybe you have a little signal that's just in between here. It would look like all just one value, even though it's very small little signal wiggling around. So you want higher resolution to resolve smaller amplitude signals. You want faster sampling to resolve faster signals. And so you can think of the transfer function here as your input signal is going to be transferred into some binary value. And so whatever this is, 1.125, let's say, gets transferred into, what is that, 4? Yeah, so this gets transferred into 4 or 5. Okay, does that make sense? So we have to visually think about this transfer function that occurs. So we can put some math around that. So there's a couple different ways to formulate this. Here we have that transfer function. We have, this is the value, the digital value out. We're going to take the number of bits minus 1, and then we have a couple concepts we got to think about. Is the oh, that should be subscript, but we have the voltage of the reference low and the voltage reference high here. And that just means what are the reference voltage ranges? So it could be 0 to 5. It could be -5 to 5. It could be anything that your hardware allows, and there's good reasons sometimes to adjust it for your signal. But in this case, we're just going to say the low digital reference here is 0, and the reference high is 5. And so here we can go through and calculate what the digital value is. And here the floor function just says, essentially, just drop any of the, because this output will give you a decimal value for bits. So it'll be like 4.21 bits. Well, your microcontroller doesn't know anything about a 0.1 bit, so it just says remove any thing greater than a whole value, a whole number. Here we go. So in this particular case, you put some value in there, say like 2.75, that's going to get translated into 4, okay? Binary value 3, sorry. There's a issue with this particular construction, and that is it's nearly impossible to get 8, right? You would have to have perfect. The way they set up this ladder, it's always going to be to the n minus 1, so it's nearly impossible unless this voltage was above 5, which we've said is not valid. We're going to go up to 5. There's no way to say that you have a value that's greater than. So what most manufacturers do, or something that can be done, is they will do offset everything by half a bit. So they'll take this whole thing and they'll shift it over. So all they did was shift it over by a half, and that allows you to round. So you're just going to round up. If it's above half a value, round up. If it's below half a value, round down. Same equation otherwise. And if you just want to see that transferred, so here, that does mean the digital value is different. That mapping is now different. Before it was 0.25 n gives you 3, I think, and now it's going to give you 4. Something like that. Here you go. So if you just wanted to use it in the same formation equation, you can still use floor. It's just adding half a bit. So all I'm trying to say is to give you ability to get to the highest bit, manufacturers will offset this transfer function, this table, by a half value. Yeah?
You can talk about how you actually implement this electrically.
Oh, yeah, yeah. Oh, to the point where you would like me to stop. What other questions you have? Okay.
Explain what the difference between those functions again?
So this one, so it depends how this transfer function was set up and what our assumptions are about where we start here. So here we have a full bits width, and then you start your ladder up. The problem here is that you can never achieve the highest bit. You can't achieve 8. Do you agree? It's minusculely small, and I have to have a voltage greater than 5 to get that. And so what manufacturers do is they offset this table by half a bit. Slide it over, okay? And so here is the equation for that. And the only difference here is you're using the floor function versus the rounding function to determine, because you're going to get something like 5.6 bits. Well, you don't have it 6 bits, so you got to round that here, or you got to floor that here, or round it here. And this is just a reformation of this function, but instead of using round, you use floor, and that means that's where the half a bit hops out.
Does round always round up, or it rounds like?
Well, 0.5, from when I went to high school, this is what they taught me. If it's 0.5 or higher, you round up. If it's lower than 0.5, you round down. My daughter's learning different math. It's exciting to be old.
Yeah.
Okay. So in this structure, there's error in the sense that if you get a binary value 1, well, what exactly was the input voltage? You don't know. It could have been any value here. We'll reduce into 1. So it's good to think about what's the quantization error? What's the error inherent in this measurement? And so here's one way to look at it. You say, here is that lattice tree we just talked about. So here's voltages and measurements. And then here is the error. So as you've got your input error, here's your quantization error. So you basically have a bit step size. So you're going to get 1.5 plus or minus half an LSB. That's the amount of uncertainty you have in your measurement. So sometimes it doesn't matter, but say you want to know exactly what's the voltage off a voltage divider for some reason, because you have to make a decision whether, I don't know, your ailerons go up or down. Well, you don't want to have an algorithm that is very, very precise, needs very, very precise values, but your ADC is taking these big chunks out. So you have to think about what's the inherent error in your measurement. And it's not like the hardware malfunctioned, it just doesn't have the resolution to get what you want. Yep. So why don't you take a minute and think about what is the quantization error and how would you calculate the quantization error? So you have a 12-bit ADC. What is the quantization error if your voltage range is 0 to 3 volts? All right, you work together for a couple of minutes, see what you guys come up with.
If you have 12 levels, don't you have 11 voltages between the voltages?
So part of this question is, what's this?
0 divided by plus or minus. To get a range of 3 over 11.
That's like, fine, perfectly fine. You learn it for the first time, you don't have to have ideas.
It'll just feel like this is.
So it's six sizes compared
Right? Like I'm getting like 0.0007.
Yeah, I saw.
Any company I could get.
If you have and you divide the
Give us any cheat sheets. He was just like, take that voltage span and tuck it into little chunks.
Yeah, just subtract it.
We're gonna have a nice little debate about that. And all the debate and how data sheets, what they're really doing inside.
This is the substance.
I guess I'll come back and ask you for a 12-bit EEC. So the data sheets will tell you whatever they don't ever even put that 1 in sometimes, even though it has to be there.
2 to 12 steps.
They're 2 to 12.
It is a lot. It's a great ADC. You should use that.
It can be well, this is like as basic as it gets.
0 and 3.
Actually, I think this is and then set divided by 2.
So you got that we split it into
Is representing
the center is 0, and then it's 1. Other fingers on your arrows increasing it to go right here.
you have 256 segments. You'd use 1 to represent 256.
Stuff in 427 or any other.
Do you think it's going to interest to do
Finally, we got that right.
It's not like yours.
his brain.
Because it's like furthest away.
What do we got?
2 steps on the
May get a the quantization error, the uncertainty, if you're given a measurement, a digital value, what your uncertainty is. Yeah.
1/2666.
How about just put it in decimals for me? Geez, I can't invert things in my brain. You only do fractions, I only do decimal, uh-oh. If I'm the grader on your exam, we're in big trouble.
3.751 e.
There you go, all right. So it's, there's quantization error, and then there's also just your uncertainty. So given some binary value, it is plus or minus this actual, plus or minus this voltage. So you can take that binary value, and you can look up in that tree structure and say, okay, I'm supposed to be getting, as the middle of that, say 7 volts. And then here it's gonna say it's plus or minus this. This is this uncertainty for a 12-bit ADC. So clearly the higher the number of bits of your ADC, the uncertainty in any one of the measurements is gonna get smaller and smaller and smaller. Maybe have any questions how we got to that number? So the game is really just to realize that you have a voltage range and you have to chunk it up on the little chunks. And so what's the smallest little chunk you have? Well, that's gonna be your uncertainty. In this case, I just said plus or minus, but you could have said double that and just said that's your uncertainty range, I guess. Okay. Yeah.
Question. So is the way this works is it's kind of taking like the floor of each of those intervals? Like, is that why you're subtracting 1? Because otherwise you wouldn't be able to represent 3 volts.
I can't. Yeah, I mean, I can't break this thing up into, like here, I can't actually get 8 transitions into here. This is why it's by -1. Right, so there's 1, 2, 3, 4, 5, 6, 7 transitions. I can't perfectly get this one. So I'm always 1 bit less. And then fake it by offsetting by half to allow you to access that bit. But you're always, the real question is, what's the variation in this voltage that will still give me a single binary value? Does that answer your question?
Yeah.
And so you get back to, if you go look at your data sheet in your STM32, they just say it's, don't put the n-1 in here. Oftentimes they don't. Because the difference between the value, this number with n-1 versus just 2 to the n, it's the same number. Like, I have to go way the far out here, and so there's just like a rounding error, like nobody cares. And so you'll see that sometimes in your data sheet is what it is. All right. So some ideas about signal conditioning. We're not going to talk necessarily about methods to do it, but you get control over the values of your reference voltages. You can set your high reference and your low reference. So if you're trying to sample this signal, you choose wrongly, right? Say you made your high reference VR plus and your low reference VR 0. And then maybe in your STM32, it would be 0 and 3.3 volts. Well, if your incoming signal is larger than that, then your signal is going to be clipped. Right? So this is the signal you got. You might think I'm getting square waves if it was clipped enough. Right? That slope was high enough. So you may have to do signal conditioning. And so that could be as simple as run it through some voltage dividers. Maybe you need an op amp to do that. Some microcontrollers allow you to control what VR negative is and VR positive. It's much easier to control VR positive. On your STM32s, you can use a power line. That would be normally 3.3 volts, although that's noisy to make it a reference because you have other things switching and power supplies bouncing around. They also give you an internal reference voltage at 2.8 volts, I believe. And that's very clean and very stable. So that would be a better way to do it if you're doing very sensitive signals. But if your signal's higher than 2.8 volts, you might clip. Some ADCs, there's standalone ADCs will actually allow you to put an analog voltage in for the V negative. And so if you think about op-amp circuits, sometimes those are plus or minus a voltage rail. Now you can have an ADC that's also in line there, plus or minus a voltage rail. Makes signal conditioning a lot easier. So it's just important to think about what's the range of your signal and what's the range of your sampling device. You have to make sure those two things line up. Likewise, your signal could be too small. And if you have a 12-bit ADC, it's probably going to be fine. You'll still resolve it, but you just don't have a lot of resolution in there. Right? So You could go and shrink your ranges, right? You could have your V plus smaller and your V minus, well, I mean, I guess that's a good place, but just a little bit smaller or a little bit higher. And so the bits, those 12 bits that are distributed would be distributed more around your signal. Here, I got lots of bits there sampling nothing that I would expect there to be. But if I did it from here to here, I'd have the full range of my signal going across all those bits. The alternative would be to use like an op amp or something to boost it into the zone in which your ADC is sampling. So maybe the ideal range looks something like this. This does make the assumption you know something about your signal. If you know nothing about your signal, then you're in trouble, because then it could go higher, lower, be smaller. But typically in most situations, you know something about your signal and you're trying to get it to be coarsely matched to the ADC that you're using. And then just to make that explicitly clear, that when we're thinking about this transfer function, this is this value here, the Vref be negative. So you can set it to whatever you want, and depending on your particular device, the hardware allows. So that's just how that idea, negative ref and positive ref, translate into this transfer function. All right, cool. Any questions on? All right. We kind of alluded to this before, but there is this challenge of the aliasing where you could be sampling slower than your incoming signal and be fooled into thinking that there's this lower value signal here. And it's such a well-known problem that almost all ADCs have a low-pass filter in it to limit the signals that can come in, so you're never fooled. You never fool yourself. That's kind of what the oscilloscope was doing when it said, I have a bandwidth of 200 megahertz, even though I can sample up to 5 gigasamples per second. It's saying, I'm not going to let you sample faster and find undersample signals and fool yourself. The challenge here is that you may be expecting a very low frequency signal compared to what your STM32 will do, and its hardware filter may still allow in higher frequency signals than you're expecting. You may have to go put in your own hardware or anti-aliasing filter. And so, beyond the scope of this class, in some ways you can ask me, Matt, or James, if you ever said, oh, these signals keep corrupting my thing, how do I get rid of this noise? We might suggest a circuit topology and give you a tutorial for your final project. I guess the other statement is, know when you have to call an analog engineer, know when you have to call an RF engineer. It's the most important part. So the answer is, do you really have to signal condition? Yes. Longer answers, but some of you don't have to. Again, I just said this, but many ADCs already have an analog filter in them. You have to read the data sheets. There are particular types of ADCs that inherently require them. And so then I think it is a SAR ADC, which we'll talk about. No, it's a delta sigma converter. It requires an input filter on it, or else you will get erroneous results. And sometimes the manufacturer puts a filter in there, and sometimes they don't. All right. This is just more details on filters if you need it. Okay. So any questions so far? I know I'm going to torture you with 2 worksheets in one class. We didn't get to it last time. All right. So here, this is how most of the world works. All right. You have some physical phenomena, and your boss at your company wants engineering units out the other side. But in the real world, you have some sensor. Sensors are often called transducers, and this word comes from you have some physical phenomena, external world, and you need to transduce it or turn it into another signal. I'm not saying the sensor doesn't, some sensors put up binary digital values, but at least the more primitive ones will translate, say, resistance or pressure into a value like voltage or current that can be measured by the ADC. So you need something that's going to transfer a physical phenomena, ideally into a voltage that can be read by your ADC. Then you have ADC counts, some binary value, and in software that needs to be turned into engineering units, something that a human can make a decision on. And so in this example, we have a temperature sensor. This temperature sensor, data sheet, that's almost the entire data sheet, I promise you. There's only two pages to this data sheet in the real world. And it says, here's a transfer function. These voltage, or this temperature results in this voltage on the output. And so your goal given a certain voltage input or a certain temperature, figure out what the you're given, yeah, what's the to go? All right, so the temperature is giving you a voltage. Tell me what the engineered units are, or what is the degrees in Celsius? Work your way through that transfer function. First question is pretty straightforward. We just did this. What's the minimum step size of an ADC? Guys can work together, be loud.
What's the transfer function you'll need to write in your code ADC values to
Up here.
That's the same from
Okay.
it's the ADC, not the actual output. Horizontal steps.
I think so. Yes, this is the, yeah,
I think if we're not calculating the error, we want to divide by position.
yes, because this is the step size, so then we would just do.
Just rewrite the situation. Well, I'm not. What's VTEP? VTEP is the voltage.
Oh, I see. Oh, so you just translate it into voltage and then translate it into the temperature.
The minimum step size in terms of temperature. It's still the minimum step size of ADC.
Just like we did before with the floor or whatever they made.
Yeah, so that's the
I should have said temperature in there. That's a much better question.
I think the step size.
Yeah, this is the step size.
Oh, one more thing. Why do you multiply by 1/2?
To write it.
Multiply by 1/2.
To represent.
So you just reverse the function they give you, right?
4 minus 1. Yeah, so then 3 by 3.
I keep typing the wrong number, that's why.
Well, then VTEP is Range of the voltage divided by 2 times the
Step.
minus
1. Certainty versus the step size.
Isn't it, and then, so this is the.
So I mean, like, I don't think this matters for 2.
Okay.
Yeah.
Your ADC value is like half of 2 to 10.
you have
Down to just 3.22
Just think that
like so whatever you measure it's in voltage. Whatever that's yeah.
the output voltage of the ADC value.
The one half is very one half is
In order to get back to
Yes, but
in your code.
figuring out the
Convert it. Well, the ADC value would just be some 10-bit active voltage in your code.
exactly.
So you just have to convert it to
I think there's
C value to temperature.
voltage
3.24, so then
to get back to temperature.
like you need to get to the ADC
You need
value.
to find this the N minus and the B is a formula.
So I mean, where
Like you need to like this is the
So how do we go from the voltage of the possible?
Find out later.
Maybe now we can go back and do it.
but I mean you have to rearrange it.
So multiply this by 0.0.
Don't worry about it.
Like yeah, I think I just don't know which one.
You will find that we will draw structures of ADC where you can explicitly look at like how it's constructed and figure out this but here you won't, you don't know. Yes.
I don't understand what this is
There's a equation to solve for.
I don't know why.
I could try that. I'm just gonna keep it the same.
No, that's fair. That's fair.
Does that mean like it won't actually be able to output like
As well as like, we don't have the volts, we have the value of the ADC.
Sample frequently enough.
I think we're supposed to like convert what would this number be in the ADC, what would this number be in the ADC. And then, you know, rearranged.
Equals this times its sample.
I just don't know what this V is.
Yeah, I don't really ADC value for the.
Wait, so did you do something different from just?
What is that equation?
It's the opposite direction. This is from ADC to temperature, going to temperature.
But if you 50 years
How many steps?
for that.
The issue is like there's some like rounding that is used to get to ADCs, so it's not exactly. We can reverse it.
You put this grounds here, right?
Normal or correct?
Yeah. I think you just want like a common ground. For D, you kind of just guess. You said you have like a word. Engineer. I just don't have enough. For some reason, you can't just say a number, everybody's gonna ask why.
It's 3.3 in the bottom.
There you go.
That's the max.
And which by power too. What makes you think that's temperature?
I don't really care, like, temperature, like, it'd be pretty slow, so we can measure very
So the other way you could say is, how fast can temperature change? Very fast. Like, in this room, how fast is temperature change?
Look at that device that keeps measuring that frequency.
I saw you trying really hard.
Yeah, because it's like I just want it to be like a real no.
That's like this one.
You said 5.
Okay.
ADC value is a 10.
Got. Alright, so what's the minimum step size? Anybody calculate that?
Is it 0.00323 volts?
Yeah. Really small, think about, you're at 3 millivolts step size. That's really small, even if you did the 12 minus, 2 to 12 minus 1, about the same size, so I cheated. Okay, what about the transfer function? Yeah?
This probably might be wrong, but I got 434.
Yeah, be really loud.
I got 434.
I went and did the math, it would be hard to do this probably give you more time if I really want to do on a test, but here's the transfer function I got out. So basically, you're just going to take, oh wait, no, I didn't give you enough. Hold on. That is the transfer function. So here you can work yourself through here. The reference, and so here's the reference ADC value. So here's the function, you put ADC value in here, you get some temperature out.